Okay. Let me start by saying this then. I'm actually not a really big fan of how we teach trigonometry in Alberta. I think we actually, the way that the curriculum is set up, I hate. If you went to a school in the States, you would have a course just on trigonometry. Okay, you're nodding. You might have like Calc 1, Algebra 1, Trigonometry 1. But in Canada, especially in Alberta, we teach you a little bit of trigonometry every year and then hope that somehow you'll put it all together at some point. And I don't like that myself. I think it's better just to teach it all at once. Because I think you guys just told me various little things you know, like say hypotenuse, rise over run, SOHCAHTOA. Like you've learned all these little skills, but you learn them like a little here and a little there and a little here. And I bet you if I were to give you a test on any of those right now, you'd crash and burn. Because of the fact that we only do just a little bit at a time. Does that make sense? So today today's lesson, I think, I'm going to start, if I can, like right at the very beginning of any sort of trig you've learned. So most of this should be review, but we kind of need to like consolidate all of your previous knowledge and put it all in one place. Does that make sense? Okay. So first slide, just definition slide. Trigonometry, the key thing I need you guys to know is that trigonometry deals with triangles. That is like the main shape we focus on. Now, are there more shapes out there than triangles? Absolutely. For example, there are squares. But I'm going to stop circles, actually. Circles, bear with me for a second. Here's a square. Look, a square is two triangles. Does that make sense? So even as a square, it's more than one triangle. Or maybe you have, maybe it's not exactly a perfect square. Maybe it's like a parallelogram. Well, I mean, we can still make it two triangles. Or maybe we can make it this triangle and that triangle and two other triangles. Like at its core, triangles actually make up more or less a, like almost every shape can be broken down into triangles. Does that make sense? Like even if you were to make a, I don't know, like a five-sided, what's a five-sided object again? Pentagon, there we go. You can make a triangle here and some triangles there. I wanted to say pentagram, but that's a different thing. Okay, someone pointed out a circle. A circle is kind of tricky when it comes to higher level math. If you guys can almost envision that here is like a shape. I don't know how many sides this thing has, but would you guys hopefully agree with me that I should be able to make a whole bunch of triangles out of this? Like, that has to be possible, right? Technically what a circle is a circle is an n-sided polygon. Yeah, that might be a little bit too far for you guys. Okay. Do you guys know what a polygon is? It's like a something-sided object. For example, a three-sided object is a triangle. A four-sided object is a quadrilateral. A five-sided object is a pentagon. Does that make sense? A circle is technically an n-sided object. Even though a circle looks perfectly round, if you were to zoom in on any given section, really what a circle is a whole bunch of different little lines. Like it's almost like an octagon that just has more and more sides to it. Does that make sense? Oh, so like a true circle, if you can ever make such a thing, really is like this, then this, then this, then this, then this. There's a whole bunch of different sides to it. And all of those different sides ultimately make up a circle. So an n-sided polygon basically means like it's a polygon that has like an infinite number of sides. There's like a million different sides to a circle. But when you look at it, it just looks like a circle. Does that make sense? Okay, that's not, honestly, I got off topic. That's not what we're going to focus on yet. But if you go far enough into like how trigonometry works with calculus, you will get to that point. I digress. My point is we're going to focus on triangles. Okay. I pulled this slide off of Sesame Street after I watched my daughter watching Sesame Street. And I love the way that Sesame Street would describe triangles. Because they don't just say that triangles have three sides. They would actually be very specific. Telemonster would say a triangle has 1, 2, 3 sides. But he'd also go on and say, but it has 1, 2, 3 angles. And I think that's important that even like my daughter gets taught that. Triangles are not just based on how many sides they have, but also on having 3 interior angles as well. Our goal then is to find the measure of sides and angles and how they relate to each other. You can't have sides without angles. Does that make sense? Now, there are some confusing shapes that you can make. Like, for example, here's an object that has 1, 2, 3, 4 sides. But it doesn't actually have 4 angles. You could almost argue that it has 1, 2, 3, 4, 5, 6 angles. You could almost argue actually it's actually 2 triangles. Does that make sense where I'm going? So we're going to focus on anything that has 1, 2, 3 sides. And often we label these sides with letters. You guys have probably learned something like this. A, B, and C. And usually convention is you use capital letters on like a corner. And that refers to like whatever the angle happens to be. And then across from the angle, the side across, is usually given a lowercase letter. Have you guys ever seen this before? Is that news to you, or is that something you know? Okay, so convention is basically uppercase for angles, lowercase for sides, and you just use the same letters across from each other. So if you talk about side A, it's different than angle A, and side B and angle B. Does that make sense? Okay. One of the first things you would have learned about at some point in your life is this first property. The sum of all the interior angles is equal to a certain number. And I totally screwed up that number on the slide. Does anybody know what it's supposed to be? Yeah, I don't know what the heck I was thinking. Whoops. So the first property of triangles, we've discovered that every triangle should up to 180 degrees. So therefore, if you ever know 2 out of 3 angles, you should know the third angle. Let me give you an example. Let's say that this right here was 110 degrees and that this was 45 degrees. If I asked you for angle A, you should be able to solve for angle A then. What would you do? Sure, that'll work. I mean, something like this, 180 minus 110 minus 45, that's going to be what angle A is. And I'm guessing that's probably something you guys have done at some point in your math careers. So, I don't know. Just do some basic math here. 180 minus 110 minus 45. I got 25. Okay, one thing I should note, when it comes to a diagram, never go based on what the diagram looks like. Like this angle right here might not look like 25 degrees. Never base your answer based on like how it looks, because it might not be drawn properly. Does that make sense? So even if it doesn't look like that's 25 degrees, base your math on that. Okay. Here's something else that I'm hoping you've heard at some point. All of the different types of triangles. Do you guys know these words? Yeah. You've seen them before? Okay, so just a quick version then. Equilateral triangles, very specific. You have 3 sides and 3 angles that are all equivalent, hence the term equilateral. Does anybody know what the angle has to be in an equilateral triangle? 60 is right, yeah. The reason why it has to be 60 is that if all 3 angles have to be the same, 60 plus 60 plus 60 is the only thing that adds to 180. So equilateral triangles are very specific. There's only 60 degrees in all corners. Does anybody know what the side length has to be? Trick question. There is no side length requirement because it depends on how big you make your triangle. There's a tool on here that can help me do shapes. Where's triangle? Here we go. So here's an equilateral triangle. This angle, this angle, this angle, they all have to be 60. Here is another equilateral triangle. Again, the angles are all 60, but the side length, like this could be 1, 1, and 1. This could be 5, 5, and 5. So like you can make a triangle bigger. If you make the triangle bigger, the angles will stay the same, but the side lengths will become bigger or smaller. Does that make sense? Okay. Isosceles is hopefully another word you've heard of. Basically, isosceles means that two sides are the same, so therefore two angles are the same. If I were to draw an isosceles triangle, just going to draw one here, it might look something like this, where this side right here is, I don't know, 70 degrees, and this side right here is also 70 degrees. The third, I just said side, the angles are 70 degrees. The third angle then is going to need to be 70 plus 70, 40. Okay. Whatever this side here is the same as this side here. This and this one are the same distance as each other. Does that make sense? Okay. Scalene is the third type of triangle. It has like no similarities whatsoever. Like none of the sides or angles are the same. Right angled means there's a 90-degree angle. Do you guys know the convention for how to draw a 90-degree angle in a triangle? Good. Yeah. Okay. You have seen this. So like it's the little like a little box kind of thing like that. That means it's 90. That's convention for that. Oh, one more thought here. Do you guys know the convention for similar sides being like a single line and like a double line to indicate that it's different? Okay. Okay, good. Acute angles. All of the angles are smaller than 90. Obtuse means one of the angles is bigger than 90. So like for an acute angle, all of these angles in here are all fairly small angles. Here the obtuse angle is like a fairly large one. But you can only have one angle bigger than 90 degrees because you can't have more than one of those in a triangle. Is that familiar? Cool, moving on. Here's some more pictures of it. I guess, I don't know, we kind of talked about that. Okay, here's the second property. You guys will have probably learned this at some point. This is the official property as discovered by, I think, Euclid was the guy who figured this out years ago. The property is the square of the hypotenuse is equal to the sum of the squares of the remaining sides. You guys know this in a different way. Yeah, c squared equals a squared plus b squared. Or do you guys learn it as a squared equals b squared plus c squared? Like, how do they teach that to you? Okay, so I'll use the first one then. Basically, the rule is that c has to be the hypotenuse. And do you guys know that the hypotenuse is the largest side in the triangle? Yeah. Which is across from the 90-degree angle? You guys heard that before? Okay. And so we always call that one C. Well, I shouldn't say always, but that's typical convention. But I've seen it done otherwise, so that would be C. And then this side here would be A. Oh my goodness, come on, Chris. This side here would be A, which makes this little a, and that would be B and little b. Okay, I arbitrarily chose A and B. You can flip A and B around if you like, but C has to be the hypotenuse, though. Does that make sense? Okay. Do you guys know why this works? You ever seen a proof for why the Pythagorean theorem works?
Probably.
Forgot. Okay, well, maybe I should show you. I'm going to be thorough today, even if it takes longer. Imagine you've got this triangle here. The most common triangle to do this for is one where this length is 3, this one is 4, this one is 5. This is probably the best triangle to start with. The way that it works is that you're supposed to square this number, and if you add these two together, it should equal that number there. The way this works is you have to almost imagine that on the edge of this triangle, you make yourself a square. And the square is going to be 3 units across and 3 units deep. How many boxes have I drawn then? 9. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 squared is 9. You guys ever seen this before, or is this still new?
Oh, yeah.
You have seen this? Yeah. Okay, well, I'll keep going then. On this axis right here, then you'd draw 4. So you'd have to make 1, 2, 3, 4. You've got like 1, 2, 3, 4, but you got to make it 4 by 4. So you got to go 1, 2, 3, 4. If I were to add up how many boxes we have total, it would be this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. There's 25 total boxes if you take these two sides and add them together. And that should always equal, if you do the exact same thing on the furthest side, 5 by 5, you guys can probably already do that math in your head, right? Is going to be 25 as well. Does that make sense? Like that's where Pythagoras' theorem kind of was originally developed, is basically counting this side right here, making a square, finding the area of this square, which is like, say, a squared, finding the area of this square, which is b squared, and discovering that it's always equal to the area of c squared, regardless of how big each of the sides are. It's really convenient with 3, 4, and 5, because it just works out perfectly. Now you know, I guess. Actually, that's my next slide. Whoops. I didn't realize I had that on there as my next slide. Whatever. Okay, 2 more properties that you guys have probably heard at some point. One of them is about sine, and one of them is about cosine. At some point, have you guys heard the acronym SOHCAHTOA? Yeah. Okay, we're going to work with that a lot in this unit here. The definition of sine is defined as the ratio of opposite and hypotenuse. And the property of cosine is adjacent and hypotenuse. Often when you guys learn this at first, we learn it as SO and ka, and then later I'll show you TOA as well. And the way that SO works is that sine of an angle is supposed to be equal to whatever the opposite side is over the hypotenuse side. Is this kind of familiar? Okay. And cosine is supposed to be the adjacent over the hypotenuse. And we'll do tan in a second. Okay. Okay, here's my important note. These things are supposed to be ratios. Like a ratio is like another fancy word for a fraction. So sine, cosine, and tan are all supposed to be ratios. And they can always be reduced to a decimal number if you want them to, I guess. So you need to be fairly comfortable working with either fractions or ratios, whichever one you end up being, given in a question. The last sentence is the most important one, though. This ratio should never be bigger than 1. There is no way that when you do like opposite over hypotenuse that it's bigger than 1. And the reason why is the hypotenuse has to be the longest side. Like by definition, the hypotenuse is the biggest side of the triangle. So there's no way that you can take a number and divide it by a bigger number and have it be greater than 1. Like if it's 1 over 2 or 7 over 9 or 100 over 101, I guarantee you this ratio is always less than 1. That makes sense? I think I just drew a random triangle here so we can just make up some examples. So I'm just going to make up an example for us to solve just to practice this. Hypothetically, let's say that I gave you an angle right here as 42 degrees. I'm going to tell you this is 90. And let's say that this side right here is 8 centimeters. Using this information, this is enough information for us to solve a triangle. You guys ever heard that phrase, solve a triangle? Basically, it just refers to like solve for all of the unknown sides and all of the unknown angles. So I'm going to use another color pen. What would this angle right here be? How are you solving it? Yeah, exactly. So take 180, take away 90. Take away 42, you get 48. Does that make sense? Okay. Well, if you understand how SOHCAHTOA works, let me just try an example here. We should be able to solve for this side right here. I'm going to start labeling them. I'm for sure going to call this side C, because it's the hypotenuse, which means this right here is angle C. And honestly, it does not matter which one is A or B otherwise. You just got to pick one. So I'll just pick this one to be A. And this one to be B. But it doesn't actually make a difference. Okay, the way SOHCAHTOA works is you have to know an angle. It doesn't matter which angle you know, but you have to know an angle. So I'm just going to go with the 42 because we already knew that angle. Okay. Compared to this 42 right here, which side is opposite? Good, you guys know this. So this side right here would be opposite. if we're talking about 42. And this side here would have to be hypotenuse then, which means by default, this side right here would be the adjacent. But that is if the angle we're talking about is the 42 degrees. Okay. What if the angle was the 48? Then what changes? And that would be the adjacent. Okay. The hypotenuse is guaranteed to be the same side, though. So one thing you may have learned how to do then is say something like this. The sine of theta is the... Actually, no, let's not do sine first. Let's do cosine first. The cosine of theta is equal to, like, adjacent over hypotenuse. Do we know a theta? Sure, we just said it was going to be 42. Do we know the adjacent side on this triangle? Good, 8, yeah. Do we know the hypotenuse on this triangle? Okay, so I'll just leave that as h then.
Nellie Wiese-Watkinson and Emma Hart, please come to the office.
So now it's basically an algebra problem. How do we solve for h algebraically? Is that louder? Yeah, sure. Take h and times it up to either side. What do you do with that cosine 42? Do you guys know? You divide it down to the bottom of the other side. Cosine of 42 is just some number. It's just a ratio. So you're going to bring the cosine 42 down to the bottom of the side here. So it's going to look like this. H is going to be 8 over cosine 42. You ever done that before? That's why we're doing this. We're starting from scratch. Okay, calculator time. One of the things that I need for you guys to make sure you do in a graphing calculator is before you do anything, press mode. There are 2 ways of measuring angles. If you want to ask a grade 12 kid about radians, probably will make them cry because radian sucks. But we're just going to work with degrees for right now. So can you guys make sure that your calculator is always set to degrees? And then next year I'll talk to you about radians. I'm going to kind of bite this off in pieces. Okay, so press mode. And it's the, top row next to second. Okay. Your calculator will default to radians. So just every time you do something, just double check to make sure it hasn't somehow switched back. So let's try this. 8 divided by the cosine of 42. Before I even press enter, tell me something about this number. Should it be bigger or less than 8? Greater than 8 or less than 8? Why does it have to be greater? Good. And I got 10.765. As a general rule of thumb, just to make things simple, always round to the 10th. Okay. I know that goes right in the face of me telling you about exact values for like the last little while, but just to make things simple, just round to the 10th. So let's call this 10.8. Does that make sense? All right. Based on that number, I now can use sine. Sine of theta is supposed to be the opposite over the hypotenuse. Do I know theta? Sure, it's still 42. Do I know the opposite? No, that's actually the one side I still don't know. But I do know the hypotenuse now. The hypotenuse is, I just solved for it, 10.8. Okay, I'm going to write 10.8, but when I do the math on my calculator, though, I'm going to use that number. Does that make sense? So in case you lose that number or like you don't write it down, have I shown you guys like store alpha A just so you can have that number saved for later? Because although I do want you to round at some point, if you keep rounding over and over and over again, it leads to inaccuracy. Like it will cause you to eventually become even more and more further from the true answer. So press stow right here right above on and just pick a letter. I just pick A. So, based on this then, how do I get O by itself? Perfect, yeah. So basically take alpha A and times by the sine of 42. I got 7.2 basically. that make sense? Is this something fairly familiar to you guys? Okay. What do I have next? Do I have another blank triangle to work with, or just some info stuff? Okay, can I do one more example? I'm going to be really thorough today, just because we are starting from the beginning.
Here's the blank one a couple slides later.
Sure, why don't we just go use that one instead then? Ooh, that's not an eraser. Use the one that's a few slides later for this next one then. Let's just make up another thing. Let's say this is 90 degrees. And let's say I tell you that this side right here is 2 and this side right here is 5. And now that's all I give you. This is enough, believe it or not, to solve the triangle. It doesn't seem like it's very much, but it is enough. If you're ever given 3 parts of a triangle, it should be enough. Let me do the angles first. Actually, no, let's do the other side first. How can I find the other side? Yeah, Pythagoras' theorem, I think you guys know it as. Have I used that word already, Pythagoras' theorem? Like c squared equals a squared plus b squared. We should be able to find the other side by doing 5 squared plus 2 squared. It's the square root of 29. I'm okay if you then actually do square root 29 to get a decimal number. So I got 5.4. But can we just say whenever we need to use this 5.4, can we actually go back and find the true value so we're not rounding? Okay. There is a way to work backwards and find angles as well. I want to make sure I've shown you that. Let me just label the sides just so we have them as like A's, B's, and C's. We'll go C here. And then let's just be consistent. Let's make that A. And we'll make this B. Do we know any of the angles? We do know one. We know one of them is 90. Okay. The only problem is we really can't use a 90 degree in our formula. So we have to solve for one of the other angles. And I don't care which one it is. I just got to pick for one to solve for. So why don't we just say we're solving for this angle right here. Let's pick the top one this time. Based on this angle up here, which sides are the opposite adjacents and hypotenuses then? Okay, so this one's the adjacent, this one's the opposite, and that one's the hypotenuse. That makes sense? Okay. Well, based on the information we have, I just need to make some more room here. I can write out one of the trig formulas. Let me do sine. I think sine will work. Sine of theta is supposed to be equal to your opposite over your hypotenuse. So I'm going to fill in my variables. How many variables does this equation have? Do you guys know? 3, yeah. Theta is a variable, opposite is a variable, and hypotenuse is a variable. So I need to plug in 2 out of 3 variables. So I need to know some of them. Do I know theta? Okay, so I leave that blank. Do I know the opposite? 2. Do I know the hypotenuse? 5.4. Do you guys know how to get the angle from this? Okay, you know how the opposite of add is subtract, the opposite of multiply is divide, the opposite of square is square root? Well, sine is an operation, and it has an opposite. The opposite of sine is inverse sine, which is the little -1 thing. You ever seen that before? Yeah. Well, just like with algebra, if you do something to one side, you have to do it to the other side as well. So that means you have to sine -1, that thing right there. If you sine -1 a sine, that just kind of cancels away. And what you're left with then is that theta is equal to the -1 sine. I'm going to start using the right word. This is called an inverse sine, just so you guys know the terminology. It's the inverse sine of 2 divided by 5.4. You guys ever use that button on your calculator before?
Yeah.
Okay. So you have to press like second sine to make it the terminology is inverse sine is the words we use. And then do, what are we dividing again? Oh, there it is. 2 divided by, okay, now 5.4 is actually not the right number. It's, I'm just going to say root 29 actually, just so I use the exact number. Anybody else get this? 20.8?
Yeah.
21.8?
How do you get the bracket way on this line? Because I just took the
Oh, yeah, you have to let me do it. Oh, okay. So then you need to do the inverse sign.
Oh.
You need that sign right there. Now that doesn't actually change anything because then you want to do 2 divided by, and then that. Here. Does that work? So that means this angle now is 21.8. Does that make sense? Okay. Let's say we wanted to find the other angle over here. You have a lot of different methods you could use then. One of them is just your knowledge that triangles add up to 180 degrees. So because they add up to 180 degrees, 90 plus 21.8 plus this angle must be equal to the leftover part. Does that make sense? Now might be a good time, though, for me to talk about the last thing I skipped, which is tan. So can we just hold off on that thought for a second and just skip back to tan? Because I kind of jumped over that bit here. You guys okay with sine and cosine so far?
Yeah.
Okay. Tan is just the combination of the two. Technically, tan is supposed to be known as the ratio of sine over cosine. But we don't teach that to kids in junior high because I think it's a little too confusing. But I want to show you how this works. Okay. Tan is technically supposed to be whatever sine is divided by cosine. Okay. What is sine supposed to be equivalent to? Opposite over hypotenuse. What is cosine supposed to be equivalent to? Adjacent over hypotenuse. You see how you have hypotenuse written twice?
Yeah.
They can cancel. This hypotenuse and this hypotenuse cancels, meaning that tan is equal to opposite over adjacent. Okay. I know it's a subtle difference, and honestly, it does not change your lives at all. But I think in junior high, it makes way more sense just to tell a kid it's opposite over adjacent. But technically, that's not actually its definition. Tan is actually defined as sine over cosine. And it just happens that when you do the math, it equals opposite over adjacent. That's all. So let me try using tan to solve the question that we just didn't use here. Let's say you want this angle right here. Have you guys ever seen that this symbol right here? Do you guys know what that symbol right here is called in Greek? Okay, good, theta. Typically we use theta to represent an angle, but we don't have to use theta. Sometimes we'll use other Greek letters. So if I'm going to define this one as theta, maybe I'll define this one as alpha. You guys ever seen that symbol before? And sometimes we just use different symbols, just so you're not using theta everywhere. Honestly, it doesn't change how you solve the question. I'm using a different letter, only I'm using a Greek alphabet letter now. Let's try using tan then to solve for alpha. The tan of alpha would be equal to the opposite. What is opposite of this angle right here? Yeah, I know I wrote adjacent for it, but now it's the different angle. So now the opposite is the 5. And what's the adjacent to the alpha? Good, okay. So then algebraically, if you haven't seen this before, let me just do it again. How do you undo a tan sign? Yeah, call it an inverse tan. So if you tan inverse a tan theta, or sorry, a tan alpha, and then you tan inverse 5 over 2, these tans will cancel, so you just need to inverse tan 5 over 2. Inverse tan 5 over 2. And that makes it 68.2, which I think that makes sense. Doesn't 68.2 fit when you add all these things up to try to make it 180? So you have options as to how you solve. You don't have to do it one way or the other. I just need you guys to know how to use all of these tools. So far, so good?
Yeah.
This feels like stuff you kind of know? Yeah.
When you use the inverse, it's just like kind of canceling the.
Yeah, so what ends up happening is if you ever want to solve for an angle, you have to inverse tan to get the angle. But if you're given an angle, you don't inverse tan. Let me just maybe write that out real quick here. Let's say that your equation is tan of 42 equals opposite over 7. Just times up 7 and go 7 times tan 42. Don't use the little -1 button on this one here because you know this angle. So just type it in like 7 tan 42. Does that work? But if it was tan of an unknown angle equals 5 over 7, that's when you have to tan inverse in order to get rid of the tan. So you inverse tan for angles. You regular tan if you have an angle. Crazy as it is, what we just talked about in like half an hour takes like junior high kids.
A year.
Yeah. You know what I mean? This is why I don't really like the way that we teach math. Because I think a reasonably smart 11th grader, I can show you all of that in like a day or two. Whereas like I think we're very inefficient by teaching you like Pythagoras theorem in grade 7 and like SOHCAHTOA in grade 8, like a little bit more in grade 9 and fair enough. You know what I mean though? Like where you do a little bit every year, I could cover that with a reasonably smart kid in like 2 days. So that's just my opinion though. I think it's wildly ineffective. So. Okay, what else should I cover? More pictures, more triangles. Here's just a slide just talking about the inverse concept. So you see how here we have 2 sides? If I wanted this angle right here, what should I inverse? How do I label these sides here? What's the 7.7? It would be opposite, because we're comparing it to theta. The 14 then would have to be the adjacent, and this would be the hypotenuse. So if you wanted theta on this, you'd say that the tan of theta would be 7.7 over 14. So if you want theta, you have to tan inverse 7.7 over 14. Kind of like I was just saying to Devin. And it makes sense?
It just makes sense.
Isn't that crazy though that like in half an hour I can explain to you all of junior high and grade 10 trig? Alright, like
I always got confused about which one was opposite and which one was adjacent. I didn't know which one, like which sine codes are tangent.
do you guys feel like you have the hang of this?
Yeah.
Okay, why don't you guys take a break? Can I try the next set of notes then? We do 2 in 1 day?
Oh, we're done doing notes.
More or less. I mean, the rest of it's just examples, but if you feel like you have the hang of it, let's move on. So take 5 or so minute break, and then let's try topic 2. Discrimination of shapes, yeah. Poor rectangles getting fun of.
What was a square?
I guess he's a square. Oh yeah, there. Okay, let's just keep going then, I guess. Okay, one of the things that I guess today we talked about was how you have to round. Rounding is less than ideal in really any science, right? Like every time you round, it's going to cause a little bit of inaccuracy. And so one of the ways we try to deal with that is work with exact values as much as we can. And so that's what I want to work on today, or I guess in the second half of this lesson. We're going to do a bunch of word problems, and wherever possible, I'm going to show you how to use an exact value. So I'm just going to hop into a bunch of examples. So here's the first one. Anybody play baseball?
Yeah, when I was 12.
Oh,
Me too.
I
The best
remember
stuff.
you.
Let's see.
Squad.
7 we played baseball.
Yeah. What?
Nice.
I was with Gabe.
Oh yeah. Sorry, buddy.
Okay, so if you guys know anything about baseball, an ideal baseball diamond will be 90 feet between each of the bases. And this makes a perfect square. I mean, I know it's technically it's a diamond, like they call the baseball diamond, but really it's a square that's been tipped, I guess. So, is there a triangle drawn? But we can make a triangle by doing, like, say, this. And sometimes this is necessary in solving a question, is you might need to take another shape and, like, make it into triangles. So my question is, let's say there's a guy standing on first base and he tries to steal second. How far does the catcher have to throw the ball from home plate directly to second base? but I want to find the exact distance. What was that?
9 squared plus 9 squared is going to equal that.
Good. Yeah, you've already figured out this is like the hypotenuse of a triangle right here. C squared equals A squared plus B squared. 90 squared plus 90 squared is C squared. Does that make sense? Awesome. So we need a calculator. 90 squared plus 90 squared gives me 162.00. Yeah, the guy didn't throw the ball 16,000 feet. What if I missed? Okay, good. Okay, so then you got to square root both sides. Now, this is a good introductory topic because we've already done exact values before. One of the things we could do is we could try leaving it exactly as this number. But we've also talked about how to like simplify square roots, radicals, by looking for like perfect squares that go into this number. For example, 162,000, I could break that up into 162 times 100. Why am I picking those particular numbers? Because 100 can actually square root. Does that make sense? Actually, 162 can probably be broken up further as well. If I divide it by 36, no. Divide it by 49. Divide by 16, nope. 4. Actually, maybe it doesn't. Well, it has to be a square rootable number, so it has to divide by either 4 or 9 or 16. Actually, I'm having a hard time making any square rootable number work. Anybody get one that works? 81 works? Makes sense. So if it's 81 and 2, then I can square root 100 to give us 10. I can square root 81 to give us 9, and 2 has to stay. So then my final answer is 90 root 2. Because you got to times the 9 and the 10 by each other. Does that make sense? I lost you there. Okay. So in terms of breaking this guy up, he breaks up into an 81 by 100 by 2. And that's what it breaks up into. 81 does square root to 9. 100 does square root to 10. But 2 is kind of left over. But then the 89 and the 10 I have to combine together to make 90. Does that help if I write it like that instead?
Why do we have to write it like that? Why can't we just like square root it and do this?
Okay, so the reason why is that that's not an exact value, right? Because at that point that number's been rounded. Even if you were to write it as, let me just square root it here. 162.00. I get 127.2792206. Anybody else get that?
Yeah.
What's the next number?
No.
There is a number that comes after the 6. I don't know what it is. There's a number that comes after that, and a number that comes after that. And so even though this number is very precise, I mean, it's got all of these digits. Technically, hopefully you see where I'm going here. Sometimes it's better for us to keep an exact value so that we don't lose accuracy, because that could cause problems. Granted, for a grade 11 high school math student, not the end of the world, right? But if you were a NASA physicist, yeah, you don't want to round. Your Mars rover is going to miss. Does that make sense? So. Okay, let's try another one here. There's a golfer, Padraig Harrington, probably based on his awesome pants. Some pretty spectacular pants. Xbox golf.
Yeah, it was so fun.
With Connect or
No, like,
Just with like the thumb controllers.
yeah.
Try to have that for PS3 or why it's
No,
something like that.
No, I'm
Okay. Is there a triangle in here?
Yes.
Where? Yeah, it's almost kind of like there's a triangle if you kind of imagine this, there, and there. Oh, and I mean, if any of you, I don't know, like professional golfers, I mean, they will use video to analyze their swing and try to find exactly where it's supposed to be to optimize their shot, I guess. Does that make sense? Right? Like you got to make sure that your arms are straight or there's a certain angle that you might want. Does that make sense? So there is trigonometry in a lot of sports, actually. Okay. What we do know is that the club is 35 inches long, so that's your hypotenuse right here. And we're going to aim for 60 degrees right here. The question I have for you is, how high should the golfer's hands be above the ground? We're looking for X. Boy, that doesn't show up very well on his red pants. Let's try that better. We're looking, no, purple's still not better. Blue, there we go. So this is X, this is 35, this is 60. So if we were to label sides, you actually did it wrong. Compared to the 60 degrees, the X is the opposite.
I was doing it compared to the 35.
Oh, okay, but you always do it compared to an angle.
Yeah.
Okay, so that one's the hypotenuse. This one's the adjacent. Does that work so far? All right. Well, we just did this like before your break. How do you solve this? We need to pick one of the sine, cosine, or tan that we can work with. We need to know about opposite, and we know hypotenuse. Which one involves opposite and hypotenuse? Good, yeah, sine. If we knew the adjacent, we could use cosine, but we don't know the adjacent. So start off by writing that sine of your angle is your opposite over your hypotenuse. Hello. You can come on in. I don't bite. Although if that's really good food, maybe I will. Okay, do we know the angle? Sure, 60, yeah. Do we know the opposite? Okay, I'll call it X. And we know the hypotenuse is 35. Algebraically, how do you get X by itself? Yeah, times 35 up to the other side. Okay. If I can give some advice here, there are two different ways that people might try to write this. They might try to write it like either this, sine of 60 times 35 equals X, or they might try to write it as 35 times the 60 degrees equals X. Anyone have a guess as to which one is probably the smarter way of writing it? Even though they're both right, one of them is probably better for a reason. The second one is probably the better choice. Do you know why? Okay, the reason why is that when you use your calculator is going to ask you to take the sign of a number, and a common mistake a kid might make is they might do the sign of 60 times 30, but you'd put like the 60 and 30 in a bracket. You might possibly make a mistake there. Now, not that you can't do that, just so long as you guaranteed like close the bracket for 60 and then times by 35. Does that make sense though? How's it working?
It's almost
Okay. Okay. So not that you can't write it the other way, but normally I write it like this, 35 sine 60, just to make sure that we know that the 60 and the 35 don't accidentally times by each other. All right, so let's try it here. 35 sine 60. There's my answer. Is that an exact value? This number right here is not, though, right? 30.31088913 is not. So what I want to do is I want to come back to this after I show you a trick. Okay. So hold off on this. This is equal to 30.31 ... but this is not exact. So I want to show you how to find a way to make it exact. Okay. The topic of today's lesson was called special triangles. There are two triangles that I need you guys to be fairly familiar with that can help us solve this issue of exact values. One of them is the 30-60-90 triangle, and one of them is the 45-45-90 triangle. Okay. You guys ever worked with these triangles before, or is this new? Okay, it's probably, yeah, I'm not surprised. Okay. Let me start with a 30-60-90 triangle. Okay. The 30-60-90 triangle is actually based on an equilateral triangle. Pretend that you have an equilateral triangle. What do all of the angles have to be in equilateral? Good, yeah, everything has to be 60. Okay. And what we do in this equilateral triangle is we're going to make all of the side lengths be the same. I'm going to make all the side lengths be 2, though. I know that seems kind of odd because you're like, well, why would you pick 1? But I have a reason why we're going to make them all 2 in a second. Okay. Then if I were to cut this triangle directly in half, let's imagine that you like cut it directly in half. You see how this angle right here would still be 60? This angle right here would now be 90. This angle would be half of 60, which would be 30. And you'd now have basically what this triangle is right here. But we actually would know the side lengths. If this side right here is 2, because the hypotenuse-ish kind of side over here is 2, if this whole length here had been 2, what happens when you cut that in half? It's now 1. Does that make sense? Well, I also can now tell you the other side of the triangle using Pythagoras' theorem, but doing it backwards. If this side right here is x, x squared plus 1 squared would have to equal 2 squared, which means that x squared plus 1 would equal 4, which means x squared would equal 3, which means that x is the square root of 3. Did I do that too fast, or can you guys follow that bit? Did I lose you? Did I lose you there? Okay, so are you okay with x squared plus 1 squared equals 2 squared, Pythagoras' theorem? 2 squared became 4. 1 squared became 1. Then I subtracted 1 from both sides. So then the 4 is now down to 3. And then to get x back by itself, I'm square rooting both sides. Is the square root of 3 exact? Yes. Right? It hasn't been rounded. It means that this side right here is now the square root of 3. This is known as one of our special triangles. Okay. And if you guys have your formula sheet nearby, you should draw it on there, because we're going to use this a lot over the next little bit. So draw the special triangle on there. While you guys do that, I'm just going to go turn off the... So here's that special triangle drawn out again. And I went back to my golfer question, because now I'm going to show you how we can use that special triangle to find an exact value on my golfer question. You guys see how where we finished, I had gotten to the point where it was 35 times the sine of 60, but it was giving me a decimal number? Well, what I can do is I can do a bit of a nifty substitution. I'm going to take out sine of 60, and I'm going to replace it with something from that special triangle. I'm going to go back up to the special triangle. Here's the 60 degrees right here. What is sine supposed to be equivalent to? It's supposed to be equal to opposite over hypotenuse. What's the opposite of 60? Root 3. What is the hypotenuse for the 60 right here? 2. Does that make sense so far?
Could you do that again?
Sure. Okay. So what we're going to do is we're going to find the sine of 60. I'm going to use this triangle. See how here's the 60 degrees? Sine is supposed to be opposite over hypotenuse. Compared to the 60, the opposite is root 3. And the hypotenuse is, it always has to be 2. Now I'm going to do substitution. Rather than writing sine 60 down below there, instead of writing sine 60, I'm going to write root 3 over 2. So watch this. We'll go down here. Rather than writing sine 60, I'm going to write 35 root 3 over 2. This is going to be my final answer. This is going to be considered my exact value. Maybe you could write it even like this. You have 35 root 3s, and you're dividing by 2. if I try typing that in, you know how the previous answer I had was 30.310888913? Well, like that's a rounded value. Well, 35 root 3's divided by 2 is that number. Only rather than it being a rounded number, this is considered to be exact. That makes sense? And kind of like Pythagoras' theorem, you know how the first baseball question, Pythagoras' theorem involved having square roots in it? You're going to always have answers that involve square roots in them. So the trick to this is you do the work in blue like I did here before, where you kind of solve, and when you get to the point where you have to type in your calculator sine 60, you don't actually type that in your calculator. You then go to your special triangle, you draw it out, and you do like a nifty little substitution where that kind of takes its place instead. And that's how you get an exact value. That makes sense for my first time doing that? Yeah, give me like a, okay. Okay, let's try more. That's why we do lots of examples. Before I go past that, I just want to show you the other triangle as well. So the one triangle I need you to have memorized is the 1, 2, root 3 triangle. The 45, 45, 90 triangle is another one that I need you to know, and it's based on an isosceles triangle. The basic idea is that this side right here is 1, and this side right here is also 1, and they have to be the same because it's isosceles. Based on that, we should be able to calculate the opposite, or the hypotenuse side, because it's going to be 1 squared plus 1 squared equals x squared. What's 1 squared? 1. What's 1 squared? 1. When you add them together, it gives you 2. So when you square root, this side right here is root 2. Put these triangles on your formula sheet somewhere just so that you have them nearby. One of them goes 1, 2, and root 3, and one of them goes 1, 1, and root 2. We can use these triangles to help us solve things exactly, rather than rounding. I'm guessing that's probably some of my further coming up slides actually, or pictures of this. Yeah. Here's a picture I found on the internet that just basically has the same information we just have. Only I think this triangle right here, it's just been rotated. Like they flipped the triangle over, but it's the same sides, right? You've got a 1, a 2, and a root 3, a 30, 60, 90. So let's try another example. I think maybe that's the best way to try this. Is let's do it again. So here is a fireman trying to reach a window, and he wants to know the exact length of the ladder he needs to do this. Okay, obviously, a fireman doesn't need to know exactly how long it is, but bear with me. It says the window is 18 feet above the ground. Where do I plot that? Yeah, like that up and down is 18, right? And it says that his ladder is 45 degrees. That's, I guess, a 90. We want to know the exact length of the ladder. That looks like that would be this side right here. I'll call it C, I guess, because it's the hypotenuse.
Isn't the top 45 degrees?
Oh, okay. You know what, though? Either way, it's 45 for either one, though. You make a good point. If it rests against the wall at 45, it's also resting against the ground at 45. Good catch, though. That would totally make a difference if the angle wasn't 45. Why don't I use this 45 right here to work with, though? How does the 18 compare to this 45 down here? What? Sorry, go ahead. Yeah, it's opposite, right? And how does the C compare to it? Good. Okay. So what I could write is a statement like this. The sine of an angle is normally the opposite over the hypotenuse. Do I know the angle? Yeah, 45. Sine of 45. Do I know the opposite? Sure, it's 18. Do I know the hypotenuse? I'll call it C. Algebraically, how do I rearrange to get C by itself? Cool, yeah, okay. So like basically flip those two numbers around. So to get C by itself, it's 18 divided by the sine of 45. In theory, you could grab your calculator and divide those two things, but I'm pretty willing to wager that it's not going to give you a nice even number, right? Like it's going to be an ugly value. Does that make sense? So at this point here, use one of your special triangles. 45 and 45. The way it works is that it's 1, 1, and root 2. What is the sine of 45 supposed to be then? If I look at this triangle here, sine of 45. I don't actually care which 45 you pick, but if you say pick this one, it's supposed to be the opposite. What's the opposite of the 45? Yeah, 1. And what's the hypotenuse going to be? Root 2. That makes sense? Regardless of which 45 you pick, even if you pick this 45, the opposite is 1, the hypotenuse is root 2. If you pick this 45, the opposite is 1, the hypotenuse is root 2. Oh, this says sine of 45 degrees equals 1 over root 2. Sorry. Wasn't the neatest thing I've drawn yet. Okay, well, rather than writing sine of 45 right here, I'm just going to take this thing and put it in its place. Put it in its place. So rather than writing 18 over sine 45, I'm going to write it as 18 over 1 over root 2. That's an exact value. That's actually kind of gross. We're going to just do one more trick for this. Could I call this 18 over 1 divided by 1 over 2? Would that make sense? Do you ever remember how to divide fractions? Okay. If I gave you 3 over 4 and you divide by 1/2, do you guys remember the idea of multiply by the reciprocal?
Yeah.
You guys recall that idea? So what we really have right here is we have 18 over 1 divided by 1 over root 2. This is the same thing as 18 over 1 times by root 2 over 1. See how I've just taken the second fraction, I'm flipping it upside down? There we go. This is my final answer as an exact value, 18 root 2s. Is that a rounded number? No, it's exact. It's exact because it has square roots involved in it, which a lot of time angles will need to have. You'll need to have roots involved. So I can check my work here real quick. First thing I'll do is I'll take 18 and I'll find the square root of 2, which is 25.455. And then I'll go back to the place where I stopped, you know, this 18 over sine 45, and I'll just check that. 18 divided by sine of 45. That's the same number. Does that make sense? Lost you still? Can you guys give me a thumbs up, middle, down? Where are we at? Slightly down? Okay. Where am I losing you?
Are those two triangles?
Okay.
Yeah.
Okay, that's the new step is what's losing you then.
Yeah.
Can't do it yourself yet.
Yeah, I just don't understand.
Okay. The basic concept is rather than typing in our calculator sine 45 or sine 30 or sine 60 or tan 60, rather than typing that in and getting a guaranteed decimal number, we're doing substitution. And we're substituting in a value off of a different triangle, off of the quote-unquote special triangles. So if you have those special triangles drawn, rather than writing sine 45 like you're going to do right here, we're going to find sine 45 as like a relationship of 1s and 2s and 3s and stuff like that. And we're just going to substitute it back in its place. And that'll mean that we don't have to work with a decimal number going forward. Let's try another example. I got 15 minutes still. Okay, so here's a scenario I was thinking of, I think a couple of years back when I was moving furniture. I don't know that you guys are like me at all. Maybe it's just because I'm a math teacher. But like, I will all of a sudden have like a eureka moment, and I'll be like, this is a math question. You guys don't have those moments, do you? Okay, so I have a chair in my house. There's a wall behind the chair. You guys don't have these moments. Okay, whatever. Imagine there's a wall behind the chair, and you want to recline the chair, But what ends up happening is that the chair is too close to the wall, so that like the back of the chair hits the wall and it can't recline. You know what I mean? And so what my thought process was here is, let's say that I can figure out the reclining angle of the chair. The angle the chair is able to recline is 150 degrees. 150 degrees of recline. If it was all the way flat, what would it be? Good, 180, yeah. Like if the chair could go all the way flat like a bed, it would be 180.
So would that be the bottom corner of the triangle if you were to like draw it?
Well, I could like draw a triangle like say this to there. Does that make sense? And like this right here, that's 150. But that's not actually the triangle I want to work with. I want to make another triangle right here. You guys see how there's a triangle kind of sitting right in here? I'll even draw it with a new color even. Okay, you guys can see that triangle in there in green that we have?
Yeah.
Basically the question is, what is this X distance right here? How far away from the wall do I have to place the chair so that when I recline the chair is actually able to just barely touch the wall. It's able to actually recline. So we're looking for X right here. You actually have two more pieces of information we can plot on here, though. It says the back of the chair is 104 centimeters. Where does that get plotted? Yeah, good. That's this one right here. That's the 104 is right there. And there's one more angle that we can plot. Good. 30 degrees would be this angle right here. Okay. Do you guys know why it's 30 degrees?
That's 150, the rest has to be.
Okay, yeah. The rationale is that if a flat is 180, like a flat bed across is 180, if part of it is 150 right here, then the remaining bit must be 30. Logan, Walker, or Tristan, do you guys remember the name of what that's called? Putting you on the spot here. I think it was supplementary. Supplementary. There's a name for it though. I want to think of supplementary. I could be wrong. We'll have to look it up again. But anyways, the concept is that these two numbers here have to add to 150 or add to 180. Does that make sense? Okay, I'm just going to redraw the triangle down here then. So here we got a triangle. This is 104. This is X. This is 30.
Mr. Forrester, can you please come to the office? Mr. Forrester, please come to the office.
Why don't we end with this example? Compared to the 30 degrees that we know right here, what is the X? Adjacent, opposite, hypotenuse. Adjacent. What's the 104?
That's the hypotenuse.
You guys okay with that step still?
Yeah.
Okay. Okay, well, if we have adjacent and hypotenuse information, which thing do we use? Cosine, yeah. So I might write this. Cosine of theta is supposed to be your adjacent over your hypotenuse. Do we know theta? We do. Cosine of 30. Do we know the adjacent? We do not. Call it x. And we know the hypotenuse is 104. How do you get x by itself algebraically? Times it up. Yeah, times it up. So do 104 times the cosine of 30. Okay, I think from what I'm looking at you guys out here, up to this step, this is okay-ish. Okay, it's the next step that I'm losing you on. Okay, so here's how you know when to do this. If your angle is either 30, 60, or 45, we don't want to try typing it into our calculators because I guarantee you it's going to be a decimal number. Like most of the time it will be. So at this point here, we're going to play a substitution trick.
So can we only play that trick when like one of the angles is one of the angles on
30, 45, or 60. Yeah, those are the only ones we can do this for, at least at this level. There might be ones you can do this at a higher level, but this will work for us.
That makes more sense.
So do we know a triangle that involves a 30?
Yeah.
Okay, so hopefully you have this written down somewhere. A 30 degree and a 60 degree and a 90 degree involve a 1, a 2, and a root 3. I might have drawn this mirror image compared to what you have. It doesn't actually matter. Where is the 30 degrees? Right there. Okay, cosine is adjacent over hypotenuse. So cosine of 30 would be the adjacent, which would be 1, over the hypotenuse, which would be
No jokes too.
2. Good. Okay, this is maybe one of the exceptions where this actually doesn't need to involve the square root, which is kind of nice. So rather than writing cosine 30, what I could do then is I could substitute 1/2. So I'm going to take 104 and times it by 1/2. Well, timesing by 1/2 is like dividing by 2. So half of 104 would be 52. Doesn't need a square root, which is kind of nice. But let's just double check them. The spot at which we got stuck was 104 cosine 30. This should...
Isn't that one angle supposed to be 60 and then 30's on the top? Or does that...
I totally drew my triangle wrong.
Yeah.
Good catch. Okay. Sorry, I'm getting way too far ahead of ourselves. Don't draw the triangle wrong. Because if you draw the triangle correctly, it should be 60, 30, 2, 1, root 3. Now did I do it right? Okay, let me try that one more time. Whenever you have a cosine of 30 now, here's the 30. The adjacent should be the root 3, and the hypotenuse should be the root 2. I totally buggered that up. I'm sorry. I'm sorry if I made that worse. Did I just make that worse?
Yeah.
Okay, so you're still just as lost. But maybe it is better now because clearly you found my mistake. So, okay. So I drew the triangle wrong the first time. Rather than cosine of 30 being 1/2, apparently cosine of 30 is root 3 over 2. So that means my final answer should be 104 times root 3 over 2. One more thing. 104 and 2 actually can divide by each other. So I could simplify that and call it 52 root 3's. Okay, hopefully this is the answer I'm looking for. Boy, I'm sorry, guys. 52 root 3's. 90.0666 kind of thing. Let me just do a quick summary here and then we'll call her a day. What I'm now going to try to do is we're going to try to solve some sort of context question, and most of them will involve either a 30, 60, or 45 degree angle. The idea is, though, that we can do a substitution. If you use this little special triangle, you got to do it right, though. You can't obviously make a mistake like I did. And what you're doing is you're substituting. Rather than writing cosine of 30 or sine of 45 or tan of 60, by the way, only those three numbers, though. Those are the only three we can do. You're just going to substitute in a fraction. It's always going to be a fraction you substitute in, and then that will give you now, quote-unquote, an exact value, which in a lot of cases is preferable.
Please excuse the interruption.
The question you
Just a
missed.
reminder of a couple of announcements.
Okay. Okay, thanks, guys. We'll, I guess, hopefully see you sometime tomorrow, all right?
Friday.
We'll pick this up on Monday.
Update for the mascot contest. The details are in the hallway on posters. The gym schedule for tonight. B girls are 3:45. A boys, you're heading